I hope you're going to find this an interesting day. There's a lot going on at the AI Centre, and it's an exciting time, particularly for AI and more generally computer science research. So I thought, for those of you who don't know too much about the centre, I'll give you a little introduction to it. I'm sure many of you are familiar with UCL, of course, but I'd also just like to remind you some of the great benefits of being at UCL, and maybe remind us why we came, or maybe why we're here. Okay, so UCL, of course, is one of the leading UK universities. Currently, I think we are the largest by student number, which is pretty huge. When I joined UCL around 15 years ago, we were, I think, 17,000 students, something like that. We're well over 40,000 students now. So the university is really growing very quickly over these years, and continues to grow. And of course, this is great, but our sort of natural home in Bloomsbury is under pressure in terms of space. So what this means is that we've been moving some of the departments and research activities outside of Bloomsbury over the years. And indeed, the AI Centre itself is not located in Bloomsbury, but down in High Holborn. And I'll come back to that in a minute. So I'm sure many of you remember or are aware that our sort of one of our spiritual founding fathers is Jeremy Bentham, and he's got this great phrase: "It's the greatest happiness of the greatest number that is a measure of right and wrong." So a very utilitarian approach to philosophy. So in some sense, I think a lot of the activities that we do at UCL really are in the spirit of this utilitarian approach. We really want to try to do things which are of impact, both in a sort of theoretical sense, maybe, but also in a practical sense, right? We really want to have social and societal benefit from the research activities that we carry out. So in terms more specifically of AI, it's perhaps worth just highlighting a little bit of the sort of broader history about AI at UCL. So here are four characters, some of whom you may know. So Jeff Hinton, the leading figure in machine learning and AI over many years. And Jeff was also at UCL as the director of the Gatsby Institute, founding director. He's since gone on to other things, some company called Google, something like that. I don't know. Anyway, so but he's been a key figure in AI over the years, and certainly some of the major research that he did was whilst he was at UCL. And Peter Diane took over from Jeff as the director of the Gatsby, and also a leading figure in AI and machine learning, particularly reinforcement learning. And when John Shaw-Taylor joined the Department of Computer Science, I guess almost 20 years ago or so, John had a very close relationship with Jeff and Peter, and we tried to John tried to set up make sure that we had a strong interaction with the computational neuroscientists and the machine learners, not just from the computer science department, but from other departments as well, including statistics and the Gatsby. And that I'm pleased to say has continued successfully over the years. And one example of that success is Demis Hassabis on the right, who was a postdoc and a student at the Gatsby, and he went on to found DeepMind, which is a leading machine learning company now owned by Google. So these are just four characters who have been influential or sort of benefited certainly from the spirit of interaction and collaboration at UCL. So on the basis of all of this, great stuff, we thought back in maybe 3 or 4 years ago, it would be good to found a new AI Centre as part of the computer science department. And that's what we did. And we launched this in 2019, pretty much 2 years ago, exactly. And this is in a nice sort of office building here. You can see we've got the first floor we're sharing with another group, the medical imaging team. But it's a great location and it's a great space. We have around 100 researchers who are looking at foundational and challenging issues to do with AI, but also some of the application areas as well. We are leading in language modeling, computer language, computer vision, control theory, robotics. So this is really a great place to be. We are, I believe, the largest graduator of master's students in the AI area in the UK, and maybe even one of the largest in the world, certainly in Europe. So around the programs we have in machine learning and AI and data science and computer vision, this is really like one of the leading centers where you can come for training. And we've graduated well over 1,000, probably close to 2,000 students over the last 15 years this way. So this is really really great. Through these activities, we've attracted very strong industrial support, and we do annually projects with over 100 companies. We've also been very active in spin-out generation, both in the computer science department and also more recently from the AI Centre itself. And it's hard to say, but we believe that the companies have been sold for over $100 million in value. A lot of these deals were private, so we don't have exact numbers, but this is quite a major grouping of companies that we've founded over the years. And we've also been founding partners, UCL, of the Alan Turing Institute, which is currently housed in the British Library. And our influence has been very strong there from the AI Centre, and we continue to play a very active role in helping the Alan Turing Institute. Okay, so what is it all about? What is the AI Centre trying to do on a research perspective? So I'm going to give you my own personal view. I'm sure others would have maybe slightly different impressions and ideas, but this is the way I like to think about it, at least. So I would like to think that what we're about is trying to replicate human abilities in communication, reasoning, interaction with the world, and other things also related to emotion and empathy. So why do we want to do this? Well, fundamentally, I think you can view the way that people or some people at least are working in their jobs as rather menial, right? So you might say, stacking boxes in warehouses or driving cars or lorries or whatever that might be, it's not really the best use of a human being. So things that we can automate, probably we should, right? Because this would free people up to do things that people are uniquely good at. Being able to have fun, socialize with each other, be creative. All of these things are achievable or more achievable the more that we can automate the things which really could be automated. So this is really part, in some sense, of the human development. You could see, from the industrial age, machines really started to replace human physical labor, and that freed us up to do all kinds of other interesting things, and continuing in this way, freeing people up from driving lorries or stacking boxes or doing really menial jobs will free us up again to do even more interesting stuff. Who knows what that might be, but it's certainly a very good, I think, direction to go to make a healthier and happier, cleaner and safer world for everybody. So that's our fundamental sort of raison d'etre. So what about the approaches to this, the philosophical approaches? How are you, in a research sense, gonna get there? How are you going to replicate these human capabilities? Well, a very successful approach in science has been the idea of reductionism. So, you can think about physical laws as being, a very good way to, a very successful way to describe how the real world evolves through time and, predict the future. And it's very remarkable that it's largely explainable by a small number of compact rules, which have remarkable explanatory capability. So you might also try to think about the way that natural systems work, like an animal. In a similar way, you might try to build a machine, if you like, from the bottom up, which is somehow replicating all of the little functionalities of that animal. And that may be a one way to go, but it's kind of difficult to find these simple rules or these simple ways to build these animals which would actually be successful. It's quite hard to do that in a reductionist sense. So the sort of reductionism approach, in some sense, you could think about it as a very explicit set of rules which describe how things work. So that approach can also be taken in an AI setting. So, for example, here maybe this is something like a diagnostic system for what's wrong with your TV, and experts might have been asked to provide an explanation as to why they take decisions like they do, and then you can write these rules down from the experts, and you end up perhaps with some kind of tree, like you see here. And this is a kind of classical rule-based decision-making system. And in a sense, this does kind of replicate the human experts' decision-making. And it's good in the sense also that we have good understanding and a full transparency as to how decisions are taken. The machine is taking these decisions, then directly replicating the decisions that the human would have taken. But the bad thing about it is it's pretty inflexible. We don't really, we can't generalize to situations that have not been seen before. If these, if the situation is not explicitly encoded in this tree, the machine doesn't know how to take an appropriate decision. So that's not very, very useful. And as you'll see, many of the systems that we want to operate with, it's really infeasible to write down, a specific tree like this in order such that every possible scenario which might be encountered could be considered within this tree. So in that sense, reductionism is a very difficult approach to carry forward. An alternative to this reductionist approach is to try to think a little bit more about, well, how do animals solve these reasoning problems and these perceptual problems? So one thing that's interesting is to think about, well, here's a human brain. Could you go into the brain and try to, build this from the bottom up and look at all the molecules and how they're interacting and build this thing, and maybe it's incredibly complicated, and you may be able to achieve it eventually, but it's a very difficult task. Now, so another way to do this would be to say, well, look, let's look at the process which created this brain, this human, this animal. And we know something about this process, right? We know that it was the genetics and sort of kind of an evolutionary mechanism in which the genes were mutated, and as the successful mutations helped the animal survive, they were passed to the next generation. And through a complicated interaction with the environment, the physical environment, this animal was constructed, and it was constructed in order to be able to, in this case, function well and survive well in its physical environment, which would mean that it would be able to see, to perceive, to act, to reason within its physical environment. So in some sense, we have an understanding of the process, in this case, the genetic process by which the organism was eventually constructed. What are the learning rules, if you like, by which you can start to build such an object like a human. But once we've got that human, it's very difficult to look at that and explain exactly how it works. So, it's difficult to explain why the human sort of classified that thing in its visual field as a snake, but it's easy to explain, well, how an evolutionary mechanism would have resulted in the creation of an organism which would actually react very strongly to a snake in its visual field. So this is really shifting the burden of modeling, going from an approach which is trying to explain the resulting object, or in this case an animal, rather to explaining the process by which that object, in this case an animal, was actually constructed. And this is really the machine learning approach to AI. So we cannot fully explain the complex behavior, but we can explain the process of construction. So as I said, there's some kind of analogy here in the sense that a human or an animal is created by an interaction between the rules, relatively simple genetic rules, and the environment. And over iterations, this creates a very complex human. And similarly, we can have learning rules about how to look at data and adjust parameters and have an interaction with that data. And over many iterations, we can learn a predictive algorithm, which again may be difficult to explain the final exactly how it works, but we can explain the process of how to construct this machine. So this is really the machine learning approach to AI. It's a data-driven approach to AI. We express explicitly the rules by which we're going to learn the parameters, at least an iteration of them. And this interaction with the data then ultimately results in a model, a predictive model for how to say perceive in the visual environment. So in some sense, it's very powerful because we sort of step back a little bit from explicitly trying to explain how to reductively explain how this thing works. So that's that's good. Of course, there are challenges around that in a modern day application. Some people might say, well, actually, I need some good understanding or reasonable understanding as to how the systems are actually taking the decisions. But so this is a very complex topic, and we might come back to a discussion of this. But certainly there are huge benefits to this machine learning approach, which is actually currently pervasive in all of the applications that you see, like speech recognition, speech synthesis. They're all based upon this machine learning approach. So this has become the dominant paradigm in AI over the last 10 to 15 years. So some spectacular examples of this are, for example, in game playing. So this was a DeepMind problem that they were looking at here. They were interested in how can you build a machine that can play this game of Go quite well. So very, very loosely, you might say this is really very difficult, but in some sense, the algorithm is quite straightforward. So you could say effectively when the board is in some state X and the machine makes move Y, if eventually the machine ends up winning the game, then you remember that. So the next time the board is in state X, the machine will make the same move Y, and hopefully it will win. However, if you were in the situation the machine was in state X and it lost by taking move Y, well, it won't do that again. The next time it will try something else. Maybe it will just randomly try something else. So this is a very simple rule, and you could imagine, with a lot of iterations, if you had enough time and enough space to store all these moves, you could actually end up with a pretty, an incredibly powerful Go playing machine, right? And effectively, this is how it works. Now, explaining exactly, why it works that way is difficult because the why will depend upon what your opponent is doing. So an explicit explanation as to why you should take that move is very difficult, except to say, well, this actually ends up giving you the kind of success that you would like. It ends up, winning the games. So the clever part here is really not so much necessarily in this if you like, non-reductive approach, but how to represent the states of the board. So there are so many of them, you can't possibly enumerate for every single state what move you should take, and you need some way to represent them so you can generalize from, say, known states to other states which might share some properties, so you can guess what the move should be for those states which you've not yet explicitly visited. And that's where the clever part comes in terms of representation. But again, it's a sort of similar machine learning approach in a non-reductive sense. So the clever part comes through this deep learning. So this is a kind of way to do AI or data analysis based upon loosely the way that we think the animal brains process data. So the information comes in the first layer, for example, this might be the visual field. So your retina is firing sort of neurons, which are representing the inputs. And then these firings go through to some other layer of neurons a little bit deeper in your brain, and they fire or not, depending upon how strongly these neurons are connected to neurons in the input. And for example, if this input contains a certain pattern, this neuron might fire. If there's 3 neurons here in some other configuration, this neuron might not fire, etc. So you can recognize the presence of certain kinds of patterns in the input at the first layer. And then as you go through these layers, you can recognize patterns or features within the features you learned before, and subsequently go down, sort of aggregating features or patterns within patterns, such that eventually, after some defined number of layers, you can start to recognize the presence or absence of global features within, in this case, the image. And then the question is, well, that's all very well and good, but how are you going to learn how strong these couplings should be between these neurons? And well, actually, there are ways to do that. It's just gradient-based training, typically on some objective function, as to how well you can recognize the object. So, for example, if you put an object into the image here, which is a chair, and you would like this neuron here to be saying is 1 if it's a chair in the image and 0 if not, well, you put a chair in here if it turns out to be, have a low probability or low value of keeping a chair here. And let's say you adjust some weights and it increases the probability or the value of getting a chair here. That's a good thing. So you keep adjusting these weights until you get the right answer here. And there are efficient ways of doing that based upon gradients across the objective function. So this is really, again, very, very complicated, and then exploring this machine to explain, how on earth does it come to this prediction is very difficult. So we don't necessarily, have a good way to explain the behavior of the system, but we do have explicit rules how to create such a system. So one of the areas that is currently of great interest is that typically these systems require a lot of training data to learn all these parameters. The number of parameters is enormous. People are talking about millions, billions, maybe trillions of parameters. This is off the scale in terms of classical statistical sort of thinking. Yes, as I said, the prediction is hard to explain. But also the machines don't necessarily have a really good grasp of the environment, either the sort of the physical environment or the linguistic, the natural environment of language. They don't necessarily understand all the things that we as humans understand. They don't understand common sense reasoning, etc. So there's a real long way to go still to make these systems more useful for humans. And also, we don't really necessarily trust them. The machines, we're not really fully understanding, how they work, and we don't even understand whether or not they're confident or not. So, having a better trust in machines would be synonymous with actually them giving us ourselves a sense of, how well they believe they solved a particular problem. So, to give you some examples, specific examples of research that's been going on, let's look at vision. So. We have a strong vision research group and the AS Centre in the Computer Science Department. And one of the things they're interested in doing is trying to understand the three-dimensional world around us and make ways and models which can actually take camera input or visual input and build a model of the world which is consistent with that camera input. So here is one company that Lourdes Agapito is involved with, which takes, for example, a video of a person and an audio of a person speaking, a voice actor. It maps and matches a mask, a three-dimensional mask, to the person's face and mouth movements. And then what they can do is they can use this understanding as to how the speech is correlated with the mouth movements and map that onto another person, and actually then morph or adjust the features of that person to speak in the way and the physical consistent way with which the voice actor has spoken that thing. So you can make essentially videos of people saying things that they never actually said before. Now, so you might think there are nefarious applications of this, and there might be, but there are also great positive benefits of this as well. So, for example, you can use this to do translation of text and the presentation of that into many different languages. So here's you can go to this website if you're interested and actually do a demo. I've done one for you. Hopefully you can hear it.
Hello World Artificial Intelligence Conference. I'm excited to show you how artificial intelligence can make a video simply from text. It works so well because my face is modeled in 3 dimensions.
Okay, so that was somebody doing this for a conference, and you're now going to see the same actor, if you like, the same physical person, but saying it in a different language.
你好，世界人工智能大会。我非常高兴给大家展示 AI 技术如何仅从文本制作视频。这个非常容易，因为我的脸就是用 3D 建模的。
Okay, so hopefully you could hear that. It was a little bit glitchy, but this, this video here, this person never spoke Chinese, right? So she's simply, I believe, an English-speaking actor, but you can end up with this, as if she's speaking Chinese, which is pretty cool. Here's another UCL spin-out.
I'm Michael from Niantic. Here's a demo of how we can perform occlusions in augmented reality using a neural network.
So what you're seeing here is a system which can, from a camera, try to understand the depth to which objects are away from the camera. So I don't know if you managed to see that, but essentially what happened there was the machine learning algorithm can essentially estimate accurately the depth, how far away an object is from the camera. So what you can do with that is you can then, if you're trying to do augmented reality, you can place objects within the scene which actually understand that, for example, they are in front of or behind a chair or a tree. So they have this understanding of the 3-dimensional reality that that is around them, and you can do that accordingly, and then make an augmented reality accordingly. Similarly, here's another UCL spin-out, which is another one bought recently. I'll try to hopefully play a little bit of this. Okay, so what's happening here is that the machine learning algorithm has learned to understand the pose, and how people are actually, humans are, their limbs are positioned according to their body. And given that, then you can do all kinds of applications. So here, these were running on a smartphone just itself. So this is pretty cool. And yeah, I believe this company was bought by Snap recently. So
the scale of digital communication.
So let's move on to some other applications. So natural language processing, we've had a pretty strong group in this. And here's another startup that UCL spun out a few years ago, and this startup is trying to understand how communication is working. So there's a lot of email traffic going on, and can you take this email traffic and have a computer to read it, and actually then make it in some computer readable sense, and you can then action on that. So I'll let these guys explain a little bit what they're doing.
Communication has reached new heights. 294 billion emails, 65 billion WhatsApp messages, and 500 million tweets are sent around the world every day. In your organization, thousands of conversations happen daily between customers, colleagues, suppliers, and distributors. This happens across multiple channels, such as email, chat, and ticketing systems. Every conversation contains invaluable information about your customers' demands, how they behave, and key patterns and trends around how your organization operates. Understanding and measuring conversations across your organization provides insight into how you are performing and helps you identify the sources of friction. This information can enable you to quickly eliminate unnecessary processes and identify opportunities for automation. Reinfer's communications mining platform can automatically identify key intents and extract relevant information to discover, monitor, and action processes hidden within daily communications. Become an intelligent organization, leveraging artificial intelligence to drive business outcomes.
Okay, so that gave you a little, teaser there. Essentially, that company has clients which are the biggest banks in the world, some of the biggest insurance companies in the world, and it is automatically, reading the communications that are going on and answering emails, giving management an understanding also what's actually going on in terms of email and communications traffic more generally, customer feedback, etc. in the whole company. So this is a very exciting area. They're doing very well. Another London-based company. But I just want to maybe finish with this final one. So I think an interesting thing that we mentioned before is that people basically are interacting with machines. So the question is are there ways in which humans can get better trust and a better understanding of how the machines are actually taking the decisions, and how can we train them in a more efficient way? So what we would like to be able to do is, we said before also that it takes a lot of data to train these deep learning systems, but maybe there are smarter ways to do the training, actually by more directly interacting with people. So people typically, have a very good understanding of the problem that they're trying to solve, and if there's only some way you can sort of, train the machine and get at that deeper human understanding more easily, that would be very, very useful, and would actually help us to reduce some of the effort that's required to train these systems. So to give you a flavor as to how this might work, so in a classical situation, let's imagine you wanted to make a machine learning algorithm, one of these deep learning systems, that could classify an image as a certain kind of animal, right? So maybe what you start with is hundreds or thousands of these images, and you'd ask somebody, a human or a collection of humans, to label each and every one of these as, this is a parrot, this is a tiger, etc. And once you've got all these labels, you would then go to this machine learning algorithm, and you start to adjust all these parameters in these deep neural networks such that the output of this system, when presented with an input image, would be the correct response. So that's fine, and this is the classical paradigm, but it's a lot of work. So the Mechanical Turk, for example, is a platform which enables people to provide these labelings for you at some cost. Now, an alternative would be to do something like this, where maybe a human might label a small number of these images. So they might say, these ones are bears, and then basically, or this one is a bear here. And the machine then says, okay, I have some rough idea of what's going on here. It looks through all the other images, which have not yet been labeled by anybody. It says, well, this is probably a bear, and this thing's probably a bear, because it kind of looks similar to this thing you said was a bear. So it doesn't ask, it thinks it knows what's going on with these images here. It looks at another image though and says, well, this thing here, I have no idea what that is. I've not seen anything like that before. Please tell me what that is. So the human says, well, that thing is called a crocodile. And then the machine says, okay, well, that's then probably crocodile, and that's probably crocodile. And, it already knows that this thing's probably a bear. And then it finds another image, which is really doesn't understand at all. So, and this process then continues, and you end up then only having to label those images that the machine does not currently understand. So rather than a priori labeling all of them, you have this interactive process, this human in the loop process, in which the machine is asking the human only to label things it doesn't understand. And what we can see is that actually, this is a little bit difficult slide to interpret, but you can actually, the number of labeled examples on the x-axis, and the accuracy of the system is on the right and the y-axis. And you can find that you can get significant savings in the amount of labelings that need to be given by humans to train these systems. So you can typically end up almost the same, if not a very similar accuracy, using a small fraction of the previous human labeling effort required. And this is cool, and with other similar ideas, we can get a much more effective way to train these systems, and that's the Human Loop company that's also doing well from UCL. So UCL also has many other interests in machine learning, for example, natural language processing. We have efficient ways to do question answering. I won't go into the details, but you can read about that if you're interested by going to the website. There's also very interesting action research. So we have the algorithm, which is called AlphaGo VR, which is actually co-discovered at UCL. And if you take our algorithm, as DeepMind did, and you go through a training process, and you spend maybe, we don't know exactly, but a lot of money to train this system, a lot of compute power, you end up with a system which can play games like Go, actually without any human experts required at all. So we don't need to sort of bootstrap the system with a human saying, oh, this is probably a pretty good move. Actually, the system can learn from scratch to play Go or chess, etc. And the system that we came up with is currently by far the best machine learning game playing agent that's ever been invented. It totally trounces everything in the past, and of course it trounces humans. Like already since 1992, the humans couldn't play chess better than a computer. But this, you're way off scale now. There's no chance that human would ever beat a machine again at any of these games based upon these systems. But they're expensive, and they're very computationally, a lot of effort required to train them. Again, the underlying algorithm to train them is very, very simple. The idea is very simple, and the iterations of this simple idea and the parameters and the learning rule, with a lot of money and compute resource, ends up with an amazing player. And so DeepMind obviously took this much further than we did, but it's essentially the same algorithm, and they're able to show that this leads to by far the best performance as you go along with training over any of the standard previous mechanisms. And this holds for a whole variety of different games. We're also very interested in multi-agent reinforcement learning. I'm not going to play a video here, but this is the idea then, how can agents or machines collaborate together in order to solve tasks? And we've looked at various game playing scenarios. There's also, this is a very sort of abstract situation here, but this is another one in which each dot represents an individual object, or which can act in itself individually or collaboratively. And the red dots, they don't collaborate, but the blue dots, they actually collaborate, and you can learn how they should collaborate together such that they can actually dominate the red points. They can surround them and win this game. So Jun Wang from UCL AI Centre, he worked with the Didi, which is like the Chinese Uber, and Didi have since used this kind of similar algorithms to then manage their fleet of cars efficiently in China to save on cost and energy. So there are real world applications of this stuff. So other work, we're very interested in things like generative models, how to produce images, speech, text, etc., which can be of great utility. So for example, this is some work from NVIDIA, and each of these images here is, these are humans, these are not actual real humans. These people don't exist. These are just computer generated pictures, and they're remarkably, human-like. And I'm pleased to say that even though this wasn't directly a UCL paper, Yan Kaut, who was the lead on this, I believe, he was at UCL as well. So most folks, or many folks who are leading globally in AI at some point came through UCL, and particularly the computer science department. We're also very interested in compression. So we have, let's say, images, and we want to compress them in a lossless way, so we can send, a much more compressed version of the image to somebody else, and they can then reconstruct totally accurately the image based upon only a small amount of sense information. And we have, using deep learning methods, we believe currently the world's best compression algorithm, and this will be hopefully extended to video and other applications in the medical sciences as well quite soon. So this is a very cool idea. Drug and molecule design, we're working on this. How can you understand and explore this space efficiently for new drugs to be designed for medical reasons? We have great researchers looking on how to do robotic manipulation efficiently, how to learn quickly, how robots can pick up objects, grasp them, and manipulate them. Obviously, great labor-saving capabilities there. Also, weather prediction, climate modeling, these are all very complicated systems which we can use machine learning to help speed up the understanding and the predictions of these complex processes. So what's the future? Well, I think currently AI systems, the progress has been amazing. We really, particularly the last 10 to 15 years, have seen an incredible success. But we're not there yet. We don't have AI systems that I would say having a really good understanding as humans do of the world around them. And we certainly need to find better ways to train these systems. Currently, there's too much labeling effort going into training these systems. And of course, if we can get around to some of the computational and the economic burden of training these systems, that would also be very appreciated. I think we're beginning to see some of the benefits of interacting in the real world. Just to give you a sense of that, one of the interesting things is that the stories I heard, I think, from another researcher, is that we can make these game playing systems, like say playing chess. Since 1992, we can easily beat a human being at the game of chess. But we're still struggling to build a machine that can pick up chess pieces on the chessboard and place them reliably into other locations on the chessboard. So what that tells you is that, in these well-defined systems like chess, it's relatively straightforward to solve these problems, or to build very capable chess playing programs. But interacting in the real world physically, which is very messy, things are not quite as accurate as your simulations might wish them to be. It's very difficult. It's much more difficult to actually make functioning, well-functioning robots and interactions. So that's really a grand challenge that we are also very excited about, and we're working on. And I think in general the future is very bright. I personally am very optimistic about the capabilities and the potential for how AI can actually remove some of the drudgery around manual labor that's going on currently, and actually free us up to do amazing things and to improve life for everyone. So that's it.
Thanks, David. There's a couple of questions in the Q&A.
Okay, so let me check. So Suraj, could this approach be extended beyond menial jobs to affect jobs that include creative thought that AI would be used to generate? I think, well, that's a difficult one to answer. I mean, there are actually currently the legal sector is going through trying to understand whether or not a machine can be attributed as the creator of a patent, the inventor of a patent. And actually, I believe that very recently in Australia, they have accepted that the creator of a patent was actually an algorithm. Whether or not you want to call it machine learning or an AI algorithm, I don't know. But the owner of the patent is not the machine; it's actually the algorithm creator. So certainly, we do see machines being used to help in creation. So you've probably seen that these are great tools that people can use to create images, create videos, but that fundamental creative step as to that's a difficult thing to really answer, right? I mean, you can ask a machine to make a story right now, and you can say, okay, you can tell the machine, please write me a story about President Bush or whatever it is, and it will write some text, which actually it seems plausible. Maybe it's not totally accurate, but it's quite good. But I don't think it's impossible that you could end up, trying to train a machine which would then create text which humans would find inspiring, interesting, funny, but maybe we need to have that as a learning criterion, which I don't believe is currently there. I don't think people have, tried to train machines with explicitly to try to surprise humans by their, quote unquote, creative capabilities. But that's not impossible. So I wouldn't be surprised to see machines almost fully automatically, with some priming from a human, be able to generate content which humans would find, very entertaining to absorb. So, so yes, I think it's possible to some degree. But there are still a loads of places where it's very, very difficult to to do that, and there's a very long way to go still. Next one from Taco: how to prepare data for deep learning? Well, yeah, that's a good question, and there are a lot of, that's a very difficult one to answer. There are a lot of let's take that situation where you want to make, say, a visual object classified. Maybe you start with objects of say animals, and you want to train a system that can recognize the animal in the image. So what that means is you need to go out there and collect images to start with, and that typically is a relatively low cost part of the process. So gathering that information, the unlabeled information, if you like, just the images alone, would typically be relatively straightforward. So that's usually the situation we're in machine learning. It's not always the case, but usually that collection phase is straightforward. But the data labeling phase, where a human has to say, actually, this is a monkey, this is a crocodile, etc., that's very, very expensive. So I don't know if that's the question you're asking, but there needs to be smarter ways to sort of do that, maybe that data and labeling collection process. But what this also means is that the algorithms also, okay, this example of the animals is not maybe that interesting, but there are other situations where you might say, well, actually, I want to recognize people, right? I want to be able to take images of faces, and I want to be able to recognize certain characteristics in the faces, either who is the individual in the face, or what is the kind of emotional, are they smiling, what's the emotional content of that individual. Now, in that sense, there are a lot of social and philosophical questions around how do you go about preparing or collecting that data, right? So, how do you ensure coverage of the kind of population that you're interested in? How do you ensure that there are no biases, etc.? So these are not necessarily directly machine learning or AI challenges. They're related to what we want to do, but there are also social challenges and philosophical and moral challenges around how to actually define criteria, which in some sense would be fair or unbiased. What does representative mean in terms of, say, collecting face images? So, and also there are questions about permission. How do you, in some sense, reliably know that the individuals that are using this data set have actually given their explicit permission for their images to be used? And if they haven't, how ethical is it to either build a system like that or to buy or purchase a system which has been constructed on the basis of data which wasn't, in some sense, reliably sourced? So there are a lot of interesting topics and questions around that data collection part. Okay, let me just have a look at another questions. So let me, for some reason, I don't see the chat, Q&A, sorry, there we are. The next question is from Supan Shah. As a final year master's student wishing to apply for a PhD next year, what are some new projects you're aiming to start in the next year? Well, the AI Centre itself is, it's vast in terms of its scale. It's probably best to go to the AI Centre website. You'll see then a list of individuals of the AI Centre, and there are links then to the research interests, and you can hopefully start that way. If you don't have any success, just send us a message, and we can put you in touch with individuals, who might be able to tell you a little bit more about what they're doing. But certainly that from the spectrum is broad, from natural language processing to vision to robotics to healthcare, etc. We're very interested in all of those things. So the next one for our Ruud Lacra, how do you see the field of machine learning evolving over the next few years? Well, yeah, I guess we are going to see more and more data, bigger and bigger systems, more computational effort, more complexity around the models which are going into these systems. I think natural language processing and natural language understanding is a good example of that, but there are similar things going on in other areas. So we've seen, basically if you take, say, text of the internet, say, including Wikipedia, and you try to make a machine learning algorithm which can just then try to predict, given the previous text, what's the next word going to come, then actually the system has to learn an awful lot about what words mean and the context that it's seen so far. And if you have a big enough data set and a complex enough model, the predictive accuracy is pretty extraordinary. So, we're seeing a lot of very interesting applications of this. So, from programming computers automatically, or creating content, or generating content, doing translation from one language to another, doing summarization of text documents. There are really, incredible applications for that. But we're still not there yet. The training effort required for this is huge. You're talking about months of computational effort and millions and millions of dollars of computer effort to go into that. But I think that trend will only continue. And so the challenge, I think the insight has been that if you can somehow leverage the vast amount of unlabeled data out there, you don't necessarily have to have people saying, this is a cat, that's a dog, this is a monkey, or what this text explicitly means. But if you can just understand the structure out there with very complex models, this is what text typically looks like, this is what images typically look like, then that's extremely helpful, such that with a relatively small amount of labeled data, you can actually have very powerful classifiers. So I'm pretty sure that will continue. And I think, we will hopefully see, I think the next big thing, one of the next big things will be interaction. As you start to see machines, robots, self-driving cars interacting in the real world, I think that will be, a real eye-opener, and we'll really start to, see some of the good and potentially, bad things that can happen from AI as we start to get machines that can understand their physical environment very well. But that will be, a huge leap forward in human evolution or sort of cultural evolution if we get that. And I would imagine that will happen within the next few years. So I realize time's up, I'm afraid, so I should probably not keep answering questions at this point, but I'll finish there. Thanks, folks.
Thanks, David. You can type an answer in the Q&A if you wish to, for the ones that you couldn't answer live.
Yeah.
So up next, we have Samuel Cohen.